Hello guys, very good evening. Welcome to BYJU'S Exam Prep, the most comprehensive preparation app for all the competitive exams. So today I am going to teach you memory design, the last part. So please quickly join and mark your presence. I hope I am audible and visible to every one of you. So please confirm me once. Yes. And once again, welcome you all to my session that is on memory design part 3. So previously two parts we discussed. We discussed about CPU connections to the memory. Yes. Arnav, am I audible? Good evening, Arnav. Fine. Thank you. And earlier I have discussed about memory interface. So the different memory chips, how we can connect to CPU, and also the functionality of RAM chip, ROM chip. All those things are discussed. So in today's session, I will discuss about memory hierarchy and some of the examples related to finding average memory access time in the hierarchy of memory system. So join quickly and mark your presence. So this is an important session and the last session in this series of GATE to 2024 Fundamentals COA. This is the last class. And in the month of June, this month I will plan some other subjects. Okay, I will keep updating you what are the topics I am going to teach in the month of June. Okay. Yes, shall I start the session? Okay, so myself, Murali Krishna Bukkasamudram, I am having 21 plus years of teaching experience, both in the GATE and also I worked in different engineering colleges. And these are some of my credentials. Just have a look. And I finished ISIP certification program. So certified as International Engineering Educator and a topper of different NPTEL courses and also mentored more than 50,000 students across the different core areas of computer science and theory of computation, operating systems, computer organization, computer networks, digital logic, and ICT. So these are the areas where I'm expertise. And if you have any doubt while I'm teaching this session, you can just ask me in the chat box. Okay. And before I begin the session, I request everybody to please share the class information with your friends and also subscribe the channel and for getting more notifications as we are providing a lot of content in the YouTube and also app classes and we are updating all the things both general sessions and technical sessions. So in the technical sessions, fundamentals for GATE 2004 is going on and also NIELIT 2023 and NIELIT plus ISRO also we are starting soon and all these things we are providing. In addition to that technical content, we are also providing guidance session, some generic sessions like post-gate guidance and also preparation strategies, tips and tricks for the gate preparation. All those things we are providing. Okay. And before I begin, you can just yeah. Arnav, thank you. And just share this information with your friends, Arnav. And free gate workshop is there. This workshop is being conducted by Dheeraj Sardana sir. He's having MTech from NIT Bhopal. He's having 10 plus years of teaching experience. And this workshop is majorly related to how to secure all India rank under 100, below 100 in the GATE 2024. It is live on 6th June at 7:30 p.m. So that is on coming Tuesday. Please make use of this. And also we are conducting a scholarship test national level for GATE exam. So this is for getting some discount on the course fees we are providing for you. That is, you can get up to 90% off on our programs. And this will be tomorrow only. That is the 4th June at 12 noon. You can register for this right now for taking a step towards success in the GATE exam. Okay. And in addition to that, this is the toppers of 2023 list. So the success is continued. I wish all the best for 2024 GATE aspirants also, and NIELIT aspirants, and also ISRO aspirants. And this is the statistics of for 2023 GATE. You can just have a look. And big congratulations to all the toppers of this list. And in addition to this, many of the people have been qualified in the GATE exam and moving forward. Okay, for the admissions. Yes. I don't know. Is there a test free, sir, or any entrance fee? Yeah. You can register. I think it's free. You can go through that registration of this. You can. It's a scholarship test. It's a free only. Now coming to the memory hierarchy. So we are going to discuss about memory hierarchy here. So in different levels of memory. So what are the different levels of memory which we have in a memory system? So generally, within the CPU there will be registers, and cache memory also it is placed in between main memory and CPU, and magnetic disk, optical disk, and magnetic tape. These are the external memories. Okay, and these are the internal memories. So what are the internal memories? What are the internal memories? So internal memories like CPU registers and cache memory and main memory. So a cache memory also there are two categories. We may have L1 cache and also L2 cache. So L1 cache and L2 cache, those are the two types of caches we use. And L1 cache is also called as the on-chip cache. So that is a part of CPU chip, and L2 cache is placed in between the CPU and the main memory. Okay, so these are taken as internal memories. And magnetic disk, optical disk, and magnetic tape are the external memories. Usually we are using these as a secondary storage devices. So when you are moving from this magnetic tape memories to the CPU registers, okay, so high level memories, then speed increases as we move up. So speed increases means it takes very less time. So accessing a register takes a negligible time, then accessing a cache memory, then accessing main memory, etc. So in this hierarchy, when you are moving from this high level memories to low level memories, okay, so we can increase the size of the memory, and the access time also increases. So it will take more time when you go for the bigger size memories. Okay, for bulk amount of information we store, in order to store, we use the secondary storage, and primary memory is used. Main memory includes ROM and RAM, as I told you. And for storing the BIOS for the ROM, and also all programs and apps, everything, operating system, everything is loaded to primary memory only, that is RAM only for execution, because CPU addresses directly primary memory. Okay, so these are the two types of memory systems we use in the memory hierarchy. And if you have any doubt, please ask me. Don't hesitate to ask, and please do share the class information with your friends. And as far as the mapping is concerned, why mapping is required? So usually the CPU generates, processor is nothing but a CPU. Processor is nothing but a CPU. CPU generate an address equivalent to main memory address. Okay, and using the main memory address, we have to map into the cache. And when the reference is made in the cache, if data is found in the cache, we can say it is a hit. If data is not found, we have to go for main memory. And there also, if data is not found, we have to go for secondary storage. Okay. So in the form of pages, we load the data from secondary storage to primary storage. In the form of blocks, we store the data from primary storage to cache memory. And in the form of words, we take from cache memory to the processor. Okay, and as and when if there is miss in the cache, that means you have to go for the next level, and you have to go for the next level, keep on going till the secondary storage. That is a highest level. Okay, so in the secondary storage, if data is found, the same thing should be made available in the main memory, so for making it hit in the next reference, and also same thing should be made available in the cache also, and that can be transferred to CPU. So this is how the mapping process is taken place all the way from CPU to different levels of memory. So do you have any doubt in this? Please ask me. Don't hesitate to ask your doubts. And here this is only just a hierarchy. What are the different types of memories available? And this L1 cache is also called as sometimes on-chip cache, and L2 cache is called off-chip. So it's a part of CPU chip. That's why it is called on-chip. And L2 cache is out of the CPU. That is called off-chip. Okay. So this is the memory mapping, and let's see memory access hit ratio. So generally, why cache is used? In order to improve the access time, effective memory access time, we have to reduce. So to reduce effective memory access time, we have to access the information very fast. Every time if you go to secondary storage access is a mechanical activity, but primary storage access is a electronic activity. So primary storage access time is very less when compared to secondary storage access. So as much as possible, if the things are available in the nearest memory location like cache, so that references are made very fast and execution is made very fast, so that computer will be speeded up. Okay, but if you go for every time bigger storages, then it will take more time. It leads to performance less. Okay, so that is the reason we have to improve the hit ratio. What do you mean by hit ratio? So for example, cache hit ratio if you take. For example, if I refer to the cache 100 times, out of 100 times, 90 times if data is found in the cache, then the catch hit ratio is 90%. Okay, so catch hit ratio is equal to total number of hits divided by total references, hits plus miss. Say for example, if you make 100 references to the catch, of course, if there is a miss in the catch, you have to go for the next level. That depends on the number of levels available at that instant of time. So 100 references, if you make out of 100 references, so 90 times it is hit. What do you mean by 90 times hit? 90 times the data is found, whatever for memory read operation or write operation. If the data is found, that is considered as a hit, divided by total hits plus misses. So that is called the catch hit ratio. Catch hit ratio is the total number of hits divided by hits plus miss. So that is nothing but 90 divided by 100. So this is nothing but 0.9. 0.9 is the hit ratio. Hope you understood. And memory access time, if you consider only main memory and cache and assume that 100% of data is available in main memory, if there is miss in the cache, if that is the case, there is no need of going to secondary storage. So what do you mean by memory access time? Usually memory access time is nothing but the amount of time taken to finish a memory read operation or memory write operation. So if you wanted to finish a memory read operation, and how much time it is taking, or if you want to finish memory write operation, how much time it takes, that is called this memory access time. Okay, do you have any doubt or any concern? Please let me know. And effective memory access time is overall on an average. For example, sometimes we get the data in cache, sometimes we get the data in memory when there is a miss in the cache, and if there is a miss in the main memory, if you go to secondary storage, again sometimes some percentage of time we go to secondary storage also. Okay, so considering all these things, hit ratio of the cache, hit ratio of main memory, all these things, effectively how much time it is taking for finishing a read request or for finishing a write request is called a memory access time, effective memory access time. Hope you are understanding. Okay, don't hesitate to ask your doubts, and meanwhile you can do subscribe the channel if you are not yet done it, and please share with your friends. Okay, now shall I move forward? Yes or no? Good. Okay, now that is what effective memory access time or average memory access time. It makes no difference. On an average, what is the overall access time of memory system for getting a word from memory or for writing a word into memory? For example, let us suppose two-level memory system, cache and memory, main memory only. That means if there is a miss in the cache, 100% you will find the data in memory, main memory. There is no need of going to disk, for example. If that is the case, what is effective memory access time formula? This is very, very important. So T suffix M indicates memory access time, the amount of time taken to access a memory. Access memory, which includes either read access or write access. At a time, we perform either read operation or write operation. Okay, and TC indicates access time for a cache. For example, if there is a reference to the cache and going to the cache location of the respective address, getting the data and reading it or writing it, it depends on the size of the cache access time. Okay, and it's all hardware dependent. And H is the hit ratio of the cache. What do you mean by hit ratio? That means how many times you are able to find the data in cache. Okay, that is a percentage of hits. That is what I told you. Then average memory access time or effective memory access time, it's like this. So H into TC, that means when certain, for example, 80% is hits. So 80% of the time we access the data only in the cache, and remaining 20%, 1 minus H is the 20%. We will go to main memory, and the same thing we will make available in the cache, so that next time if the same word is referred, so that will become a hit. So for that reason, we will write TM plus TC. TM is the main memory access time and TC is the cache access time. Hope you understood. Now, one example I'll tell you. Let us suppose TM is equal to 200 nanoseconds. That means the amount of time taken for main memory to access. The amount of time taken for a main memory to access is 200 nanoseconds. And TC is the amount of time taken for cache memory to access is 20 nanoseconds. And the percentage of hit ratio is 80%. What does it mean? For 100 references, 80 times the data is found in the cache only. Only for 20 times you will go to the main memory. So 80% is the exact hit ratio. If we improve the hit ratio, effective access time is reduced because majority of the time it takes less time. Okay, so for improving the hit ratio, what measures is to be taken? That is a separate topic that we'll discuss in some other occasion. Okay, like locality of reference. For example, CPU has got more number of references for a certain program location. If that type of instructions or data, if you are able to keep in the cache, so that more hits will be there. When more hits are there, less number of times you go for the next levels. So that as the cache access time is almost 10 times less when compared to memory access time usually, so that we can effectively access the memory system in a very less time. So average access time or effective memory access time will be less. Yes, Aarti Siman, good evening. Thank you for your response. Okay, now for this case, I think you can easily answer. So average memory access time, it is written here. 80% of the time it takes only 20 nanoseconds, and remaining 20% of the time I have to go to main memory as well as cache. What is the need of this cache? Because after accessing a data from memory, we will make this same data available in the cache, so that if the same data is referred next time, it will become a hit. That is what one type of policy in the cache. So this 80% of 20 plus 20% of 220. So 80% of 20 is 16, and 20% of 220 is how much? 44. So 16 plus 44, 60 nanoseconds. For example, if a cache memory is not there, for example, and hit ratio is not there, then effectively every time you have to go for a main memory. So it takes 200 nanoseconds. But 140 nanoseconds of memory access time has been saved here, reduced because of introduction of the cache and because of improving the hit ratio up to 80%. For example, if you take 90%, for example, let us suppose if I am assuming let h is equal to 90%. So 90% means more 90% of the time you are getting the data into cache only. So effective memory access time is equal to, so 90% of the time we take only 20 nanoseconds of time. Remaining 20% of the time we have to go for a main memory of 200 nanoseconds. Again, same thing should be made available. Not 20%, sorry, it is a 10%. 1 minus h is nothing but 10%. So this is nothing but 0.1. Okay, so 0.1 into 220. So it is 18 plus 0.1 into 220. That means 18 plus 22. 18 plus 22, how much is the value for a 90% hit? Okay, it is that 40 nanoseconds. An increase of 10% hit ratio is a reduction of 20 nanoseconds in the effective memory access time. Earlier it was 60 nanosecond effectively, now it is only 40 nanoseconds. 20 nanoseconds we could save by improving hit ratio to 90%. Hope everybody understood. If you have any doubt or concern, please let me know. Okay. Yes. And one more example. If you take 3-level memory system, for example, L1 cache is there, L2 cache is there, main memory is there. So first we refer to L1 cache. If there is a miss in the L1 cache, we go for L2 cache. If there is a miss in the L2 cache, we go for main memory. Like that we mentioned. Any doubt? Any concern? Please let me know. Okay. So in this, the CPU is containing L1 cache. So that is the part of the CPU chip, and L2 cache is placed in between a main memory and cache, and main memory and CPU. And first CPU refers the data in the L1 cache. If there is a miss, we go for L2 cache. In the L1 caches, we may have two categories. In the L1, you may have the I cache and also you may have a D cache. I cache is for storing only the instructions, and D cache is useful for storing the data items. And both comes under the this L1 cache only. Okay. Now coming to TL1 is the time to access level 1 cache. TL1 is a time to access level 1 cache, and just a moment. And TL2 is a time to access level 2 cache, and TM is a time to access main memory. Then H1 is a hit ratio for L1 cache, H2 is a hit ratio for L2 cache, and effective memory access time is like this. The formula you can just carefully observe. H1 is a hit ratio. When there is a hit in the level 1 cache, we directly access the data from level 1 cache. When there is a miss in the level 1 cache, 1 minus H1 entire thing, this one. Okay, when there is a miss in the L1 cache, then only either L2 or main memory comes into picture. If it goes to L2 and L2 also certain percentage of hits will be there. If H2 is a hit ratio of L2, then we have to access the data from level 2 cache, and same thing should be made available in level 1 cache. So TL2 plus TL1 is added for H2 plus 1 minus H2. This is the when there is a miss in the level 2 cache. When there is a miss in the level 2 cache, we have to go for main memory. So that is a TM, main memory access time plus level 2 access time plus level 1 access time. So these three are added. This is for miss in the level 2 cache. Okay, so like that we can go. If I tell you an example, you will understand here. So this is that example. So calculation part you can do. Just I will show you how exactly the values can be considered. A memory system contains three levels here. Okay, so L1 cache is there, L2 cache is there, and main memory is there. And hit ratio of L1 cache is 0.8. So that is H1 is given as 0.8. Okay, and hit ratio of L2 cache, so that is H2 is given as 0.9. And this will be taken only when there is a miss in the L1 cache. And L1 cache access time is 2 nanoseconds. So TL1 is nothing but access time for L1 cache. Time for L1 cache is a 2 nanosecond. It is a very less time. Okay, and L2 cache access time is 20 nanoseconds. So that is a TL2. TL2 is equal to 20 nanoseconds. Okay, and main memory access time is 150 nanoseconds. So T suffix M is the main memory access time. So that is 150 nanoseconds. Now, what is the average memory access time or effective memory access time? Here, absolutely no difference between average memory access time and effective memory access time. So in a short form, I am writing average or effective memory access time is equal to H1. For example, 80% of the time we are able to find in L1 cache only. What is L1 cache access time? Only 2 nanoseconds it takes. In addition to this, if there is a miss in the L1 cache, 1 minus H1, so that is a 20%. In 20% of the case, either L2 or main memory. If you go to L2, only certain percentage of hits, so 0.9. So 0.9, there is a hit. When there is a hit, that means access time of L2 cache, so that is a 20 nanoseconds, and same thing should be made available in the L1 cache. Plus, when there is a miss in the L1 cache, where I should go? Just a moment. Just a moment. So 0.2 into all this. So plus 0.1, 10%. When there is a miss in the L2 cache also, we have to go for main memory, which is 150, and the same thing should be made available in the L2 cache, so that is 20, and also through L1 cache we access. So this is the total time. So effective memory access time, have you estimated it? If so, please do it. 0.8 into 2, it is a 1.6. 1.6 plus 0.2 of 0.9 into 22 plus 0.1 into 172. So this is what we are supposed to calculate, and please let me know what is the final answer. So 1.6 plus 0.2 into 0.2 into, so what is the 0.9 into 22? 0.9 into 22 is nothing but 19.8. 19.8 plus 0.1 into 172. So it is 17.2. So 19.8 plus 17.2, it is a 37. 1.6 plus 0.2 into 37. So what is the 0.2 into 37? How much? 7.4. 1.6 plus 7.4. So finally it is a 9. So effective memory access time is 9. So 9 is the effective memory access time or average memory access time, 9 nanoseconds. Everybody okay with this? Is this calculation is correct? Any mistake is there? Please let me know. Are you following this? Okay. Shall I go for the next? 19.8 plus 17.2 is taken as 37 and 0.2 into 37. Okay. 74 means 7.4. 20% of 37 is 7.4. 1.6 plus 7.4 is 9. Exactly round figure 9 we got. Okay. That's it. Now that is how we calculate the effective memory access time when there is a different levels of memories. Yes, Sirisha. Thank you. Good evening. And can you do this problem? Yeah. Assume that for a certain processor, a read request takes 50 nanoseconds and a cache miss. So finally, he mentioned that if there is a miss in the cache, it's a 50 nanoseconds and 5 nanoseconds and a cache hit. Suppose while running a program, it was observed that 80% of the processor's read request result in a cache hit. The average access time in nanoseconds is certain processor, a read request takes 50 nanoseconds and a cache miss and 5 nanoseconds for a cache hit. Are you doing it? So what option is the right option? 80% of the processor read request resulted in a cache hit. So 80% of the time it's a hit and 20% of the time it is a miss. Are you doing it? So effective memory access time in the same page I am doing. Effective memory access time is equal to, so there is 80% of the processor read request resulted in a cache hit. So 80% of the time, how much time it takes? 5 nanoseconds for a cache hit. So directly for hit ratio it is given. And 20% of the time cache miss, that is a 50 nanoseconds. Okay. So it is a 4.0 plus 10 and it is 14. Option C is the right option. Yes, option C is correct. And do you have any doubt or any concern? Please let me know and please try to share the class information with your friends. And please do subscribe the channel if you have not yet subscribed it. And I hope every one of you have enjoyed the session. And with this memory design, I am concluding. And we will be coming up with the new series. So I will be taking digital logic, computer networks and theory of computation series in this month of June. So I'll begin from 12th of June and I will keep updating you all the sessions in the Telegram group and other channels wherever you are present. And please try to attend all those sessions. And before concluding, all of you please go through this and subscribe the channel and press the bell button and you can get the notifications. And if you really liked this session, please do like it. Thanks a lot. Thank you very much. See you all. Good night. We shall meet again. Thank you. Bye bye.